Okay, welcome to Chapter 8. This is the fundamental topic for most of the things that we study in physics, because most things that we look at in the physical world are moving. It's all about that movement. So all the work of Isaac Newton in the 1600s, not actually what he was researching, but what he's most famous for, amongst many other things. So we're going to look at his laws in this section, just really the introduction to the concept. The laws are quite simple. You'll need to know what they mean, but you won't need to be able to recite them. You need to know pretty much the key parts of the laws and use that and apply that. Okay, so we're going to look at Mike that we've got here on his bus, because Mike is the mass that we're going to look at. But in the meantime, let's get started on the chapter itself. So, in terms of Section 1, when I open this up, there's not a lot to it. Okay, we've got the space for the three laws, and we're going to walk through an example here. So, really that's it. It's lots and lots of examples, both in the generic term and actually breaking things down. And it's the breaking things down that matters. Okay, so where we struggle with this is really trying to think, what is actually happening in this case? Okay, and that's where the laws come in. So I'm actually going to go back and start at the odd place, which is Newton's third law. The third law is actually the most important. Without the third law, nothing else would happen. However, in terms of usefulness, it's the other two. Okay, so being able to apply it is important. The third law is really important for us because normally humans and animals experience the third law more than the others, but it's so common that you don't realise it. So let's work it backwards. We have on the PowerPoint the proper definitions, full definitions. I'm going to paraphrase them and think about them in a slightly different way. Okay, so in the first one, what we're going to look at is objects in general, and we'll call it that idea. We'll use that language that you got from GCSE, which is an inertial mass. Okay, so a mass has inertia, and that follows on from Aristotle a long time ago in the ancient Greek philosophy, but actually he was wrong, but we still use some of the terminology. So inertia was the idea of how hard it is to move something. So it still kind of works, but yeah, at GCSE you had that. So I'll just go back. An inertial mass, what? Well, what will it do? Newton's law says that basically it will do nothing unless overall there's something making that change happen. Okay, so basically the easiest way to think about this, I think, is that the inertial mass will remain at rest, stationary. So slightly longer, but I think it makes slightly more sense. So it will remain stationary or continue on with the same. I'm going to pick up the real detail here. The word to use which links it all together is velocity, but I'll explain and break that down. So obviously it's to do with speed, but it will remain going in a straight line. Okay, and that's the crucial little bit. So keep the same size of speed, magnitude, and it will carry on in a straight line, which is the natural behaviour of all objects, what we don't experience on Earth. Okay, and come back to why. Unless, okay, and that's the crucial bit, unless acted on by, and this is the crucial bit as well, an external force. External force. Can't write and speak at the same time. Okay, so it needs to be, typically it needs to be the neatest word. So an external force, let me just get rid of that little bit up there to make it make more sense. And pick out that I think I might have actually, nope, run out of Tipex there I thought. Okay, so that external force, but it needs to be, don't forget, can be complicated. I'm going to put in brackets resultant as well, because it may be more than one force, but you put them all together, if they cancel out, there's no resultant force. But if they don't cancel out, then we get that. So what is that basically saying? Really spelled badly there. I'll change that in my notes. What is that really saying? Well, it means that if you've got some sort of resultant force, I'm going to change to a different colour here, basically, and again I'll keep in brackets just to remind you, but if you think of it as at the simplest level, forces cause change. Okay, if there is no force, if there is no overall force, a resultant force, nothing changes. If it's moving, it will carry on moving. If it's going in a straight line, it will carry on in a straight line. If it's sat still, well, it has a velocity of 0, it will remain at 0. Okay, so that's the kind of the crucial bit. So let me just neaten that up. You can tell it's been a long day. So external, that's much better. Okay, so that's kind of the important bit, but on its own that won't do anything. I'm going to skip past Newton's second law because really that's just the maths that comes from this. Okay, the third bit is more important. So what the actual law states is along the lines of for any action force, for any force that you have, there is an equal and opposite reaction force generated. Okay, so if you push on something, that thing will push back, but it won't push back until you push on it in the first place. So things will react when you do something to it, and this effectively is what causes or tries to cause the conservation of energy. So this is a bit more complicated than that. Energy is conserved, and this effectively is the reason for it, but there's a bit more to it. That's what I'm saying. So crucially, how do we think about it? Well, I think it's easier to expand this one out. So when an object, okay, so whatever that object is that we shall call A, let's make it simple, exerts a force on B. Okay, B could be a table, could be an object, could be the ground, it doesn't really matter. But when A pushes on B, that causes, and that's the crucial bit, that causes B to exert an equal force, an equal size force, or magnitude if you prefer, an equal size force basically back onto A, so on A in the opposite direction. I've put that in so much detail because people skip over the words when you say it nice and short. So A is the action, B pushes back, it reacts, and it is an equal but opposite, equal size, opposite direction. So it's basically trying to stop A producing the force in the first place. Okay, so you push on your chair, this is you, you're pushing on your chair B, B pushes up against you, it stops you from moving. Now if a different person, a smaller or a larger person sat on it, they would exert a different force and the chair would react and push back differently. So if they're heavier, so if they've got more weight, more force, then it will push back harder. Okay, the chair will still support them. And so it's reacting exactly as you push on it. And it's this that causes the chain of events that makes things happen. Okay? The crucial bit about this, and there's two ways of thinking about it depending on the type of force, is it's usually, put in the point, at the point of contact. Okay, so if you've got contact forces, when you push on the ground to move, the ground pushes back. Okay, pushes you in the opposite direction. Sometimes though they're not contacting. Things like gravity. The Earth is attracting the Moon in orbit, but the Moon is also attracting the Earth back. So things that fall to the ground are because they're being attracted by the Earth. So actually the Earth does fall backwards or upwards towards the object as well. Newton's second law means that we don't observe it, but we'll come back to that one in a bit. Okay, that's just to do with maths. So something pulls on something else, something pulls back. So either at the point of contact, but a stick in brackets, or forces at a distance. Okay, so they are never going to be in contact, but anything like air resistance, yeah, pushes back because you're pushing on it. That kind of idea. Now it's not quite that not quite that simple. There's a bit more to it. Okay, which is then when we bring then to Newton's first law. So if you are pushing on your chair and you push too much on your chair, you're too heavy for it, then it will push back with the same size force, but that will change the structure. The structure won't hold it in place, so it collapses. So you will have a resultant force. If they are the same size, there's no resultant, nothing changes. You sit on your chair, everyone's happy. But if A on B means that the B is not strong enough, or rather the seat is not strong enough to exert force B, you know, if you're a larger person, then what you'll get is a difference. It cannot be there, that will no longer exist, and you'll get a resultant force that causes you to accelerate downwards, change your motion. You won't go at the same speed. You will probably go in a straightish line, but you'll go faster and faster. You'll accelerate because of that force. So those are both crucial, and that one's the most crucial. This wouldn't happen unless you've got this in the first place. I'll explain with examples. Okay, the second law. We'll work through this. In fact, let's do this now. So, what do they mean? Well, forwards, backwards. If they cancel out, then your object will remain stationary. If you've got one bigger than another, then it will begin to move forwards, as many of you said before. You will, of course, accelerate forwards. Forces cause acceleration. If they cancel out, it will carry on moving at the same speed. But if the backwards force is against you, resisting you more than the force moving you forwards, then you're going to slow down. So it all depends on the relative size of the forces. And that's why we don't talk about balancing. Always keep saying, what do they add up to? Because then it makes this much easier, or use of these much easier. Okay, the third law is about the idea of floor and so on. So here's the idea of the chair and so on. Again, going back to the chair, there's a chain of forces. So you are being pulled down by the earth. The earth is being pulled up by you. Okay? That means that the chair pushes into you because the earth is being pulled up. So it's a chain of things. The chair is not really where the third law is, but usually we think about whether in contact because it makes it a bit easier, but actually they don't need to be because they're at a distance. The earth is attracting to you. However, because the chair is pushed up against you, you can feel that force, especially after a while and it's a bit of a stiff chair. Normally you don't notice it. You're so used to being pushed by things. You stand on the floor, it pushes up against you, but you don't notice it because you're so used to it. Okay. However, if the floor's moving, then you really do feel those forces pushing on you. Example in a second. Third one, which for us is the second law, is just simply the mathematics of it. Now, what we actually say is that the rate of change of momentum of an object is directly proportional to the resultant force applied and takes place in the direction of the force. Kind of links everything else together, but momentum we haven't covered yet, so we will just stick at the moment with the cheaty simplified version that you use at GCSE, okay, which is forces cause things to accelerate. Please notice acceleration can be at the same speed, because acceleration is rate of change of velocity. So if you change direction but at a certain speed, so the speed is constant but the direction isn't, that requires Newton's first law. You need a force to change your motion to stop you going straight and turn you in a different direction. Okay, so Newton's second law is probably easier to think of it in terms of what its effect is. So the change in velocity of the mass above, okay, whatever that object is proportional to force applied, okay, fairly obviously if you push harder your speed will increase at a higher rate, okay, so the change in velocity of the mass is proportional to the force applied, and I should say rate really, but well, we'll stick with the change, okay, force applied and inversely proportional, and this is quite a useful way of thinking about this, proportional to the mass. Okay, so bigger objects will accelerate more slowly. They've got more inertia, which means that they're harder to move. Well, let's think about that in a different way. If you've got more mass, you have more atoms, okay, because it's down to atoms and relative atomic mass, you know. But if we say more atoms, well, if you've got more atoms to move, to accelerate, you're going to need a bigger force, aren't you? Okay, so the force is proportional to the mass, or more commonly experienced, that acceleration, that change in velocity is inversely proportional to the mass. Okay, so that is kind of a more user-friendly version. Basically, there's no other factors, and at this level, if the mass doesn't change, then we can use this equation. Unfortunately, usually mass does change as well as acceleration. So if you had a rocket, for example, if you had a car, it's getting less massive because you're using the fuel. The fuel is being burnt. The mass of your car changes. Whenever you've got something to do with motive force, it's usually using something, some sort of fuel. So that is a simplified version. So let's make that really clear. Okay, so 3 laws, working backwards, F equals ma. Basic idea, if you have a force, it will change, acting on a mass, it will change its acceleration, but the mass, and this is more useful for us, the mass will also change the acceleration or the force, different ways of thinking about it, whichever's convenient. Okay, so the mass has an effect. That's really what Newton's second law is about. The first one, well, if you do have that force, then you know, forces cause things to change. We know from chapter 1 or 2, I think it was, for materials, it's obviously going to change the shape of springs and so on. So it can change shape, but in terms of movement, it changes velocity. It's that simple. Keep it that simple. Forces change velocity. Okay? That will also still work with the fuller version. So forces change velocity. Great. Okay, so let's actually think about what they mean. Sorry, in the third one, almost forgot then. What that means is A pushes on B and B pushes on A. So in my little clip, cat pushes on grass, grass pushes against the cat. It's where they're actually pushing against each other. However, are they, and this is the crucial idea, are they a pair of forces? Or are they just forces that can change size? If they're a pair, okay, so if you have a force, it will always have a second one trying to stop it. They will always be the same size. So that is the crucial, that's the only thing that's working on Newton's third law. Okay, so let's have a look at some examples for those. These on their own, as I say, you can word them in all kinds of different ways. It's the meaning that matters. So you're looking for these clues as you go through, and maths for the second one if we sum that up. So lower down, okay, I've got these things here. That is the way to think about that, and that's just a very full step-by-step version. Okay, so have a go at the remote control lorry question in the workbook. That'll really sort them out. The third one is what makes people think. Okay, so that's about Newton's first law, really. That's the thing that most people think and notice. So, back to my picture at the beginning. Here we go, wheels on a bus. At the moment, the wheels on the bus are stationary. So, if they're stationary, then what happens is you're stood on the bus. Okay, you get onto the bus, you pay your money, you stand there in your big shoes, and what happens is that you are pushing on the ground, and the ground or the deck of the bus is pushing back equally as much. Nothing is changing because this is your weight down here. Let me just put it on. So that's our mg. That's always going to cause an action, so that usually causes most things. Okay, that action means that the floor pushes back to stop you sinking into the floor. Okay, now the bus moves off. The bus accelerates. The crucial thing is Mike here has mass. Okay, so that mass has inertia. It doesn't want to move. And that's the natural state of things. It doesn't want to change what it's doing at the moment. That's the golden rule with most things in life. Okay, so maybe it is accelerating. Here we go. If our bus is now moving forward, well, what happens is Bob is basically stayed or trying to stay in the same position. Okay, his body mass is staying there. Unfortunately, the bus has moved forward, and the bus is making our feet accelerate. It doesn't make Bob accelerate because Bob is not attached to the bus. But if his feet, I mean, look at the size of them, they're not going to move. So those feet are now fixed to the surface of the bus, and because of that, what you get is not what most people think, but where you get your contact is you are going to have some friction. Okay, this is actually the accelerating friction because of something's happening. So that is making your boots move forward. That idea of accelerating force, let's keep it simple. Okay, that accelerating force moves the boots forwards, makes them accelerate forwards, but your boots, if this was as slippery as ice, would stay still. The bus would move forwards, your feet wouldn't, because you haven't got it. So what happens is you're actually getting the effect of friction holding it there, and that is what moves you forward. Okay? You and your inertial mass has to accelerate because your boots pull down on your legs pull up on you, etc. and what you feel, as this is a really fast bus, is that you feel like your legs are being stretched away from you, and that's because you are being pulled by this changing force. That changing force you suddenly notice, but your feet have moved forward, and so you're pulling backwards on the boot. Your body pulls backwards on your legs, but your legs pull you forwards there. So this kind of chain of forces is Newton's third law. Okay, they're all connected together. That's what causes it to happen. Newton's third law, up and down, still there. Don't worry about that. But that change makes you experience it. It's that Newton's third law chain that makes you feel way like you're being pulled away. If the bus then slows down, you've got the other effect. However, you now accelerated up to the speed of the bus. If you've got your constant velocity, your bus is going in a nice straight line, then again you get to this position. You're moving at a steady speed, whatever that speed is. Your bus is moving at the same speed. You do not notice any difference between you, and so you do not feel any force. You still have this force, but it's just normal. It's your normal experience, so you don't notice it. Okay, but you've still got these pair of forces. If you then slow down, well, you get the reverse of speeding up. Your body is still trying to carry on at velocity v, but as this skids to a halt here, your feet, okay, you're trying to move forward. It's the friction, again, that's stopping you whizzing through the window of the bus. So the friction on your feet is then going through a chain of forces, a chain of third law forces, to make you feel like you're being pulled out of your feet. Okay? So that's a good example, a reasonably good example of Newton's laws. You're accelerating because there's a force on you. Accelerating, decelerating. If the bus was full of people, okay, so we've got Bob sat down, another Bob, a few more Bobs, all with their shopping, you know, lots of bags and so on. So there's a lot of mass in the bus. What you'll find is that Bob will not decelerate, will not accelerate negatively with the same difference. He's much happier. Okay, we're still getting this effect, but this will be smaller because the acceleration is smaller. The acceleration is smaller. So because there's more mass, our acceleration stays the same. Changes to meet that mass. So you won't feel as much force because it's harder to stop the moving. It takes longer. It's a deceleration at a more gentle rate. Okay, so that's Newton's second law. It's the effect of filling the bus up. Okay, or of course Bob being heavier, because that will also increase the forces. Okay, so if you've got more mass, either of Bob feeling the forces pulling on him, or more mass on the moving objects, then that again changes it. You know when a bus is full because it moves off really slowly. It's hard to accelerate. So that's really kind of useful. Let me give you another beautiful example which really help, I think, sort you out. Okay, and what I'm going to do is I'm going to break it down. So this time it's you stood in a lift. Okay, and as you stand in the lift, you get in the lift, and what happens is the lift goes up. There we go. So let's say it's going up in that direction. You're going to accelerate with the lift. You move with the lift fairly obviously. When you get in, you feel normal, but when the lift moves off, you feel heavier. You get pushed down onto the floor. Yeah, and if it brakes very sharply, you kind of lift up into the air and lose your weight a bit. Obviously, your weight doesn't change. Okay, one hopes not in the lift, but you'll find that you effect of it is noticeable, and what you're feeling is not the weight. You're feeling the difference in the force here. Is it a big force? In which case you will feel like you're being crushed up, so you'll feel heavier because it's pushing harder against your legs. Or is it a little force, still lifting upwards, but maybe the force as it slows down gently, okay? Or maybe even it's a downwards force, even though it's going up, in which case the floor's being stretched away from you, you feel lighter than normal. Okay, so it's all about what you feel when you feel heavy or light. It's all about how hard things are pushing on you, how much reaction there is. Okay, so let's work that through in terms of our notes. Here's it on the back there. There we go. So, talks you through the bus. Use the ideas on the bus. It's what's going on in this section here. So I've broken it down into Newton's third, second and first law. However, how would you do a question? So if we're going, and just to make it clear, we're going up. Okay, so floor is lift is going up. We'll work it through. So first step, you stand on the floor. And you can speed up this if you want, because a lot of it is in the notes. It pushes up. mg. So that's your normal state. Then it starts to accelerate. To accelerate, you need something to happen. So number 2, you need an accelerating force. Okay, so and just to make it clear, because you'll come back to me and go, why have I got those numbers? So step 1, then step 2. Okay, to move you up, and this is the crucial bit, is to move you up, because it's all about you with all these examples. To move the person, to move you up, the force from the floor, sorry, I've just put from floor, the force from the floor must increase. Okay, so you need an accelerating force. So let's be precise here. In addition, so you've still got Newton's third law going on, okay, but in addition to equaling mg, so you've still got your Newton's third law thing. You're still stood there on the floor hasn't collapsed, hopefully, but you'll need an additional force to make you accelerate upwards. Okay, so the force must increase in addition to that for, let's just link it in really clearly, for acceleration. Okay, so at this point, how much does it accelerate? Let's follow the story through in a logical process. Number 3, the force on your feet, let's do it proper version now, force on your feet, sorry, pushing on your feet, let's be precise, will depend on F equals ma. Okay, so depends on your mass and the lift acceleration, or lift's acceleration. Excuse me while I just go and close that door. Trying to work around each other. There we go. So number 3 is that. Obviously, things are going to happen, but even still, we'll keep working on this. Number 4 follows on from this, because the force pushing on your feet is increased. What that means is, number 4, you feel heavier. You experience more force more correctly. So, number 4, you feel heavier. You are not heavier, you are still mg, but you feel heavier as your legs react to the extra force. Okay, so the floor is now pushing on you rather than you pushing on the floor. The floor is now pushing on you, pushing you upwards, and so your legs push down heavy. It's that extra force acting on you that makes you feel heavier, even though you're not. Obviously, you haven't got space to add a great deal more, but if we just go back to 5, the next logical thing, once you've finished accelerating, okay, you tend to reach a steady speed. So once at a steady speed, you, should we say again, experience no force, but of course it is not that, it is no additional force. So you just feel like mg again, you're back to there. Sorry, let's make that a different bracket. Okay, as per normal. Great. What you'll also find, by the way, chain of forces of all of this, because the lift pushes on you. Well, why is the lift pushing on you? Because it's being pulled up by a cable. So during this stage, the tension in the cable also increases, equals the same amount as the floor pushing upwards in total. Okay, whether it's on you on your own or a group of you in the lift, the floor pushing up in total must equal the tension. So when we're at this stage, then there's no additional tension in the cable. So NB, also tension in cable equals, again, not very scientific word, but it's that idea of its normal size. We'd better put in the lift as well, actually obviously has mass, and we'll just multiply that by g. Okay, so yeah, the weight of you and the weight of the lift, and that's its normal thing, normal state. So final part then, to bring it all in, that gives us our full story in reverse when it's starting to decelerate. So if you are then decelerating, the force from the floor must decrease. Okay, and because of that you feel lighter, etc., until you reach a steady speed of 0 and you just feel back to normal again. Okay, so that's the kind of process. The only additional bit is the kind of, and I say I'll put it as extra, but it is again fundamental and more common in most questions. More people in the lift. Okay, so obviously everything gets scaled up because you've got extra mass in there now. So if you've got more people in the lift, what is the effect? It takes longer to accelerate. Okay, in other words, its acceleration is lower rate, so your speed builds up more slowly. So it takes longer to accelerate to the constant, this constant speed, to the steady speed. Okay. Crucial thing is, go back to this idea, you experience less force. Okay, so again, it's a kind of a chain of maths, because there's more mass, so the chain of mathematics, because there's more mass, that means for the tension in the cable you get lower acceleration, bigger M, smaller a for the same force, which means that your bit of mass will have less acceleration, and because of that you will experience less force. Okay, so again, that idea of acceleration. So it is all less noticeable. All of this effect is less noticeable if it's a load of people in the lift. So if you do get in a lift, try and get in on your own, you'll feel the difference. And again, if it's got a bigger acceleration, you'll feel a bigger difference. So try and get in a fast lift, a high-speed lift in a tall building, and you'll feel all this going through. So have a think about it. it's not a straightforward forces happen, there's a bit more to it, but actually if you break it down, it's all kind of logical. Yeah? Thing keeping you in place, keeping, pushing against you because you've pushed against it. Then to make things happen, you need that additional force, that extra force to make it happen. And because of that, you will experience it. Humans, I should say, will experience it. Okay? So if it wasn't about you, you wouldn't even consider about what you experience. You'd just say, oh, it's accelerating, so there's a force. Great. Keep it simple. So everything happens to you because it's the lift acting on you. So think about what the forces are doing to you, and it gets much easier than trying to just talk about forces in general. Okay? So, crucial point, the forces on you. Okay, so big chunk, big hard bit. The rest really of the topic is, for this level, is just the maths of it, so it's a bit easier. We will go into this in very specific circumstances, so we'll break these down because A, they're more common, but they're also better examples when we start getting into the end of year stuff where we move into year 13. Okay, so let's leave it there. Have a think about those, try and get them clear in your head. Whenever you're experiencing a force, think it through, see if you can break it down into first, second and third law. Okay, and again, final point, you will not be asked to name them, but you will say where examples of them are. So if I just take my sheets that I've just lost somewhere, bear with me, there we go. All you need to do is go, this is happening here, and that's Newton's first law, or Newton's second one, or Newton's third. Okay, so have a think about it. Is it about things changing? Then it's Newton's first. If it's pairs of forces, it's Newton's third. And how much it's changing, that's Newton's second. The maths. Okay, let's leave it there.